we've selected a 1/2 inch pipe, and the key item we want to look at there is this highlighted red box, which is delta T saturation temperature in Kelvin. So that is the equivalent temperature for our pressure drop in that pipe. So what this means is at 1.1, at our compressors, the saturated suction temperature will be 1.1 Kelvin lower than what our evaporating temperature is on our lowest temperature suction, lowest temperature evaporator on that suction pipe. So say we have a meat counter in a deli area, and that's evaporating at -10 Celsius. This would be 1.1 Kelvin lower than that, which means we would be evaporating at -11.1. Or in this, if we are evaporating at -6 Celsius, it'd be -7.1. So moving on from there, we have our product selection for our bits of compressors. We've got a single low temperature compressor and 2 LSL 1K and 2 medium temp 2KTE-5Ks. Just put some design parameters in. Low temps evaporating at -30 Celsius, which -22 Fahrenheit. We've got a small amount of useful evaporator superheat and then 15 Kelvin of non-useful superheat, which is what it picks up in our suction line. And then the same again on our medium temperature as well. And then we've got a gas cooler outlet temperature of 37 Celsius and an intermediate pressure in our receiver of 38 bar. More importantly, what that gives us are these key values, again highlighted in red, our evaporator capacity, our power input, and our discharge temperature without any additional cooling. So we've got a COP of 1.43 there. It's not too bad. It's not great, but this is peak condition. I don't mind.
Welcome to CO2 Experts. Once again, thank you so much for joining us. I have a CO2 expert here with today, one of my good friends, Chris Griffiths, and we're going to be diving into pipe sizing for CO2 systems or R744. This is one of the things in refrigeration that is the most crucial step in design, in troubleshooting, in service, because we need to have good flow. We need to have the least amount of pressure drops. We need to have oil coming back at all times, so our compressors are always lubricated, components are lubricated. I'm excited about this because we're going to be diving into when there is piping problems, what do you need to do to fix them? Chris, welcome to CO2 Experts. How you doing, brother?
Thanks for having me, Trevor. It's nice to be on here. We've done some CO2 Mondays together in the past, and for those who know, we carry out a good number of design courses across the world together. So hopefully we can share some of our knowledge with you all today. Ideally aimed at more of a practical on-site perspective for pipe sizing and ideally helping you solve some issues you may run into versus how to design a system from scratch. I know from my experience and training, when you're a technician on the tools, you don't get exposed to the reasons behind why a lot of the system is as it is in terms of design, particularly with pipe sizing. And I know that when I made the jump from technician to design, there were not a lot of resources out there to be able to actually figure out how pipes were sized and if they were correct or not. So hopefully from today, we should be able to give you a shortcut at least and help you along that journey as well.
This is one of the things that me and Chris talk about in our design course, because this is vital for designers as well as technicians. And when we're doing a design training, we talk to the designers about how to relay this information to contractors, to end users, because I think that's one of the most important thing as a designer, Chris, as we talked about before, is being able to communicate properly with your customers. And piping is always one of the things that can either have a system run really, really well or run into major issues either at the startup or down the road where people are like finding problems, and then it takes a while to figure that out. So that's something that we definitely stress, is making sure that pipe sizing is correct and then reviewing it with your team.
Definitely. Everyone knows what looks good when it's installed. If it's nice and tidy, it's ID taped, insulations all the way through, no tears. But in terms of if it's been sized correctly, is there an excessive number of bends? Are they too short radius rather than long radius? There's all sorts of issues that can occur, and we'll run through that shortly. So if I jump through to the next slide to start us off, hopefully this is a nice, easy reference point for everyone to refer back to if you want to. If a pipe's too small, it's not going to carry enough refrigerant for it. If it's too big, not only have you spent loads more money on a pipe you don't need, it's also going to suffer in terms of getting the fluid flow for your oil back to your compressors. We'll go into a bit more in depth at the moment, but these are the common issues I would see if I was designing a system or attending a site where they had issues. These are the sort of things we can narrow it down to. So if we go through the list, we've got pipe diameter is too small, and in a more scientific term, that means that we have insufficient mass flow through that system. In most cases, if we don't have insufficient mass flow, what we will have though is excessive velocities, because we're trying to shove as much of this refrigerant through in a tiny space in one go, and that's going to cause whole lots of issues. Mainly it's going to wear the inside of that pipe surface away, which will then get carried over to your expansion devices, back to your compressors, or sit in your oil sump. And if it's coming up to expansion devices, you're going to get liquid hammer as well on the liquid line, which is, as anyone's seen, if in your house, if you turn your faucet off too quickly, those pipes will shake. It's going to be the exact same in your refrigeration system. On the other end, if we have our pipes which are too large, mainly on the suction, we're going to have very poor oil return. We rely on that velocity in that suction, in that gas, to entrain oil from our evaporators if they've made its way to there, carry it all the way back to our compressors. And normally we're going to be working against gravity in some cases. So we need to make sure velocity increases yet again when we're working against gravity to make sure it gets back to where we need it to. If there are too many bends on our system, fluid flow is going to bounce into the corner of that and redirect. That's going to increase pressure, a pressure drop. Same with having too many or not long radius bends. And for those who are aware, the more pressure drop we have, particularly in the suction, the lower our evaporating temperature at our compressor, or our saturated suction temperature at our compressor will be. That increases the lift our compressor has to do, increases the compressor ratio, and uses more energy. More energy, more money. To save your customer some more money by making sure that pipe work is nicely designed. On our suction side, if we don't install oil traps on risers, we'll get poor heat exchanger performance because the oil will stay inside those evaporators, coats the surface a bit, and less heat transfer flows into the evaporator and reaches the refrigerant. And also eventually that oil will build up at that part of the system, and eventually your compressors will be starved of oil. And another one, less so as a design, because we would, as a designer, assume that all the insulation is going to be installed correctly. But when you get to site, sometimes I've seen it that even though you specified 1-inch wall lagging, the installers have tried to save some money and gone for a slightly thinner wall. Fortunately, that's a lot more heat buildup, more non-useful superheat enters your suction, but also you'll find sometimes if you're working with low temperature applications, it will start to sweat and you'll get condensation forming on the outside of that pipe, again, leading to more issues. But
So
in terms of system performance, sorry, Trevor, go ahead.
Yeah, I have a few questions on that one. One of the things about insulation, and that I learned from you and Nabil was that you have useful superheat and non-useful superheat, and you can pick up a lot of non-useful superheat through the suction pipe insulation. So a lot of people think, well, I got insulation on it, it's not gathering any heat or it's not generating heat. Do you want to talk a little bit about that? Can a suction line pick up heat even though there's 1-inch insulation on it?
Yes, definitely. So, for example, in a supermarket, if you've got a long pipe run and it goes through from the sales floor over a bakery where there's lots of ovens, unless you've accounted for that in your design, you could effectively double the amount of heat being added to that pipe because our temperature difference has gone from 20 degrees Celsius up to a sort of 40 degrees Celsius into our pipe work, even more so if we're, again, working with low temperature. It's just a case of not just copy and paste from a previous design you've done, actually look at where that pipe is going to go and account for it as well.
Yeah. And that's something that I even learned because I've done tons of installations, putting pipes through bakeries or warm areas or really hot spaces. I just remember even being working up there, and it's so much hotter there versus on the sales floor. As well as the oil traps is another big one. Like a lot of people ask me, well, Trevor, it's CO2. Your suction's running at 400 psi or 30 some, 25 bar, 30 bar. Why do we need traps in the suction line? Because the pressure is so high. Do you want to elaborate a little bit on that, even though it's CO2?
Yes. So I've got a slide on this later on in the
Okay, good.
in presentation, but just up front, it's more important when we operate at part loads. So if we have one evaporator, absolutely fine. It's normally going to be on or off, or there'll be a slight drop in it when it's overnight. If we have a row of 10 cabinets and 8 of them are satisfied, but 2 still need cooling, lo and behold, there's a lot less mass flow to try and push that oil back up the riser, at which point eventually that riser will fill, but there'll be insufficient pressure behind it or insufficient mass flow, and eventually those 2 cabinets will starve because there's no fluid movement in that section, and eventually we'll start to achieve high temperature alarms alarming out. So hopefully part of this presentation should alert some technicians out there that if you're getting oil issues, it could well be due to the fact that an oil riser has not been installed correctly or at all.
I love it.
So let's jump on to the first one, which is what happens if we have pipes which are too small. So I think that's probably what most people are going to find rather than the other side. If you want to cut costs when you're installing, you're probably going to look, oh, can we get away with a 3/4 inch pipe there instead of a 7/8, or 1 1/8 instead of 3/8? So as we go through, there's quite a few issues that can occur from insufficiently sized pipes. So number one, insufficient system capacity. If we're not getting that mass flow through, we're not going to generate as much cooling as we actually need, and therefore we're not going to achieve temperature in our cabinets or our cold rooms. We're going to have excessive pressure drop, which, as we've already touched on, reduces our saturated suction temperature, leads to increased energy consumption in the compressors. That there has a knock-on effect with increased discharge temperatures, and it may be a case of then your condenser's undersized, or your gas cooler in this case, particularly on an LT system. Have we got an intercooler or some sort of intermediate rejector? Is that now going to be too hot to then go into our medium temperature compressors and thereby increase the discharge temperatures there and have that knock-on effect? That then leads to oil issues. Our oil is going to be running too warm, and then that leads to compressor failure. And then on the other side, more of an issue with liquid lines, excessive noise and vibration, liquid hammer, and excessive wear on those internal pipe surfaces. So just to summarize on all of those, if that pipework is too small, some or all of those issues could be present. If you're only getting 1 or 2, process would be to go through and find out or rule out the typical steps you would do. Are our compressors working? Have we got oil in them, etc.? If we add oil to a system and then go back 2 weeks later and find, well, there's no oil in our reservoir, but there's no signs of oil leakage anywhere across the system, and we also find actually only a handful of fixtures are not achieving temperature rather than all of them, it may be a case that oil is being trapped somewhere, and then we have to look back at this side of things. So what we're going to do in a second, it's going to get quite technical. We're going to look at an MT only pipework analysis on a dual temperature rack using appropriately sized pipework versus incorrectly sized pipework. So we're going to look at the correct application. It's only a small one, so we're literally looking at 1/2 inch pipe. And then we're going to look what happens if it was only 3/8 pipe. And then we'll also have a look what if it was 5/8 pipe and slightly too large. There's a lot of numbers, I'm just bracing you all now, but stand by. Just seen a question in the chat, Trevor, as well. So pipes outside diameter is going to be the same size as the next. Some pipes are thicker to handle more pressure. Is this something we have to be aware of? Yes. So if we're looking at, for example, standard gauge copper pipe versus K65, where K65 will be a thicker wall, yes, there will be a difference in capacity on that flow. So most of the softwares out there will take that into account because each pipe work will have its own internal roughness factor and an actual usable cross-sectional area. And then next question, what about compressor piping? So Carrier recommends inverter traps or compressor suctions due to liquid migration, but hadn't seen this in the field from an OEM build yet. So is that looking more, I believe that's looking more plant component manufacturing, which is a bit beyond the scope of this as a technician side of things. Should we tackle that one at the
Yeah, I
end,
think,
Trevor? Back to
yeah,
that one.
we'll jump that in the
So
end, but that's a great question.
yeah, so that's getting a lot more technical then, I think. So we're going to be looking a bit more on what that does to the compressors as well.
Yeah, it's a great question. We'll dive into that one afterwards.
So just to bombard everyone, multiple different pieces of software here, all combined just to put it all onto one page. So we've got a small system, which I'll show you shortly in terms of how it all combines. But we've looked at a section of pipework. We've used Danfoss Cool Selector 2 for this and Bitzer's software as well. So the idea of this is we'll look at this pipe size and then see what impact that has on our compressor selection and what our coefficient of performance would be as well. So we've selected a 1/2 inch pipe, and the key item we want to look at there is this highlighted red box, which is delta T saturation temperature in Kelvin. So that is the equivalent temperature for our pressure drop in that pipe. So what this means is at 1.1, at our compressors, the saturated suction temperature will be 1.1 Kelvin lower than what our evaporating temperature is on our lowest temperature suction, lowest temperature evaporator on that suction pipe. So say we have a meat counter in a deli area, and that's evaporating at -10 Celsius. This would be 1.1 Kelvin lower than that, which means we would be evaporating at -11.1. Or in this, if we are evaporating at -6 Celsius, it'd be -7.1. And I always bother Trevor with this, but I don't know the conversion factor off the top of my head to Fahrenheit. I want to say it's around 14 or 12 Fahrenheit. I'm sure someone can correct me on that.
Yeah, pretty
So
close.
moving on from there, we have our product selection for our Bitzer compressors. We've got a single low temperature compressor and 2 LSL 1K and 2 medium temp 2 KTE-5Ks. Just put some design parameters in. Low temps evaporating at -30 Celsius, which -22 Fahrenheit. We've got a small amount of useful evaporator superheat and then 15 Kelvin of non-useful superheat, which is what it picks up in our suction line. And then the same again on our medium temperature as well. And then we've got a gas cooler outlet temperature of 37 Celsius and an intermediate pressure in our receiver of 38 bar. But more importantly, what that gives us are these key values, again highlighted in red, our evaporator capacity, our power input, and our discharge temperature without any additional cooling. So we've got a COP of 1.43 there. It's not too bad. It's not great, but this is peak condition. I don't mind. Let's see what happens if we had a 3/8 pipe instead. Well, from this, you'll see actually that pressure drop goes from 1.1K equivalent to 5.4. And what that does, immediately it drops our evaporator capacity down to 12.2. Our power input stayed roughly the same, slightly up, and our discharge temperature has gone up by about 10 Celsius. And our COP has gone down from 1.43 down to 1.28. So just by changing the size of that pipe, we've had a very large impact on our system's performance. And this is how important it can be. Most importantly for me, I would see our discharge temperature has gone up quite considerably. That's where you may start to run into real issues on site with your oil management. So that looks horrible for a technician to try and carry out in the field. You would need a laptop or a very capable smartphone.
Yeah.
What can we do instead? Well, there's not a lot we can do in the field. If you're up against a problem like this, you need to start jotting some information down and then doing some homework. So unless you can see immediately, if you go from a 5/8 pipe down to a 3/8 pipe and back up to a 5/8 pipe, well, there's obviously going to be some sort of restriction, excessive pressure drop there. But what do we have to do instead? Well, we need to do some good old-fashioned starter level engineering. So we go back to basics and we carry out heat load calculations on our system. Hopefully, you don't have to do this from first principles. You should be able to find the information from the manufacturers of what's been installed on site already. So if we know exactly what evaporators are in our cold rooms, we can find the manufacturer's data sheets for that. For an example, on the right-hand side, I've used a Kelvin cooler, which I would have used quite a lot in the past, a KEC MX40-6, and we know that can do 4.2 kilowatts at whatever conditions we said, -6 or 10 or -7 with an 8K delta T on it. And then we'll have a look for these display cabinets as well. So on here, there's two which I've selected for our system. We've got a 6-foot and a 12-foot cabinet, and that's at 3 and 6 kilowatts respectively. And then the fun part happens where you have to sketch out and trace every bit of pipework feeding back to that system. Well, if you're in a supermarket, hopefully it's a large one, you can just point in the ceiling and trace it through. Or you might be in a small convenience store where it goes through 3 extra retail units down into a basement under someone's garden and pops back up in a machinery room elsewhere. It could all be quite a bit of fun. From there, note down those sizes, take account of as many bends as you can, and then we'll start trying populating some software. So the Danfoss one I like to use in demonstrations of these because it is free. It's accessible most places in the world, although it's very slow to do large systems. There are paid softwares such as White Rose MicroPipe, which is excellent for this, and you could analyze a system in probably 20 minutes if you became proficient with it, but it is a paid subscription. But if you encounter one of these issues and you fix it, it's probably well worth purchase. And once you've got all that, to check if you're having issues with the compressors, put that information into your compressor software and see if it puts them out of our operating ranges. So let's say we've traced all that pipework. Here we go. We've got 2 display cabinets and a single cold room. Nice, easy, simple system. And for the purpose of this, let's assume that all 3 fixtures are not maintaining temperature. We've already weighed out the refrigerant charge. We've already checked oil. We've checked that ambient conditions are okay. It's not outside of its design envelope. Ideally, you'd have an operations and maintenance manual on site, and you can check back to that for the initial design. But I'm sure many of us can attest to that. When you actually need one, they're never to be seen, especially at 2 o'clock in the morning when you've got a store shouting and screaming at you to get their systems back online. So what we'll do, if we assume that all 3 cabinets are faulty, well, the only thing shared between all 3 there is that main run from that last point back to our compressors. So let's look there to begin with, and we can start to model that section in a bit more detail as well. So Danfoss allows you to put each individual section of that pipe into play. So we can start with a horizontal section, followed by a 90-degree bend, another 90-degree bend. So that'd be for the bottom of our riser. A vertical section, top section where it tops out, horizontal, comes down, along, down, along, etc. And based on half-inch pipe, this gives us a total pressure drop of 1.1 as we looked at earlier. How easy is that? For doing this, we'd populate as much of the information as we could. If you don't know this on site, ideally it should be designed to these sorts of levels. So we're looking between 5 and 8K useful superheat, which is what's inside your evaporator, assuming we have electronic expansion valves which can sort of maintain that target. And then additional superheat, we try and go between 15 and 20. In some people, we go up to 30 Kelvin, which would be 50 Fahrenheit for additional superheat. And by that, we mean non-useful superheat. So that heat which we pick up in that suction pipe work through the insulation. And then on
Which
our
can be good
medium
for CO2 compressors, because we know CO2 compressors, especially the low temp ones need higher superheat than standard HFC compressors. So sometimes that can play to your benefit in your design, but we see more and more designs with either plate heat exchangers to protect them, that extra protection for those compressors. And
Yeah,
that
if you
has
know your system, yeah, you can take that into account. As you say, Trevor, the stuff which we used to rely on for HFC, most of it can still sort of apply for pipe sizing, you just get smaller sizes. But as you just said, different technologies and different components are coming into play, and it does mess with your rules of thumb slightly.
Yeah, and then you got to size accordingly to that, because you might have the best pipe sizing, but if you make a mistake on that plate heat exchanger or something that's going in there, that's gonna mess up your pressure drop. So, or components.
Yeah. So here we go. We've got our value there. But again, that's what happens now if we go for 3/8 pipe instead. And lo and behold, that 1.1 has become 5.2. So from that, we can effectively guarantee that is an issue with that pipe size. Just seen it. Ah, so yep, someone's already jumping ahead of us in the chat here with what to do next. So what if we had 5/8 instead of 3/8 or 1/2 inch? Here we go. So let's go 3/4. Let's say they've massively, possibly oversized it. Well, that saturation temperature, which is towards the bottom right, is no longer an issue. And we have very minimal pressure drop here, 0.1 Kelvin, yeah, 0.2 Fahrenheit. But what we do have now is potentially too low a velocity up our riser. So rule of thumb previously that people have worked with is you drop your riser size on the vertical either 1 to 2 sizes below your horizontal. CO2 is a bit more forgiving than HFC in terms of carrying oil back to the compressor. We don't often find we need to step it down. I've designed a lot of stores out there where, yeah, you've not needed to whatsoever. But then sometimes you fall into the risk of people getting complacent and thinking, oh, because we didn't do it on that site and didn't do it on that site, well, we don't need to for this one, despite what the design drawings say. And then they'll put the same pipe size in and then wonder why at part load conditions, all those cabinets on that island start to fall over sideways. Yeah. Not naming any names, that's fine. There's always some fun arguments of that on site.
But
So
that's
this would be a main
being
concern I
important
would
to
see
the
this
detail, right,
oversized.
Chris? Like, not, like you said, not being complacent in it, because it can get repetitive what we do as a technician, as a designer, as an engineer, because we see it day in, sometimes day in and day out in your role. And sometimes you can get complacent, because I know I've done it before. So it's important to look at those fine details on projects, because not all projects are going to be the same. Things will change sometimes, even in the design. I've seen this happen multiple times where this was I remember this one time where we were designing a store and we looked at the prints and there was 3 feet of a case over a door. You know what I mean? So it was like placed on the map wrong, on the store map, like doing the install. So things sometimes have to change, or there's a revision before the store starts and you don't have the right documents, as well as don't change the pipe sizing. If you're a technician, don't just go ahead and change. Oh, just like Chris says, oh, well, last time it was 1.3 inches. Let's just go 1.5 inches. That'll be a bit better. Because I've had people reach out to me and say, well, the foreman said, let's go with 1.5 inches because that's what he did on the last store, but didn't take into account that it was 100 feet less, or, you know what I mean? And then all of a sudden, now there's oil issues. And that's where you got to get into these softwares.
Definitely. What I've noticed, even the best intentions for customers to make sure every store looks the same, and the sales floor may look identical, but back of house and in the warehouse areas, cold rooms, completely different. And almost always you'll have something different. I was waiting for at least one day where I could remember back to one design I've done and just copy and paste at least the pipe sizing, but it never came. Hundreds and hundreds of stores and designs, not one matches another. And these are in fairly standardized stores for a customer. I can't imagine trying to do it in some of the less standardized stores across other estates.
Yeah. And then we got another question: is Cool Selector 2 a good software for pipe size? Yeah, it's a great one. It is a good one if you want to do like single piping. So it does take a lot longer versus like micro pipe. You use micro pipe, it takes all your piping. So you could have hundreds of pipings, and you change a pipe, it will effectively change all the design, or at least notify you what pipes now are undersized, oversized, things like that. So that's the difference between like micro pipe and like Cool Selector 2 or another sizing software out there. Great question, William.
Yeah. Yeah. So with pipe sizing from scratch, it's a very iterative method unless you have some good software for it. So if we look back to this, we would have a pipe section coming off of that cabinet, off of this one, and then they join together, and then they meet this one for the evaporator here, and then you have this section here. And whilst only five, probably six sections we'd have to model, if we change the size on one of those, because we found actually that's one size is insufficient, that will change all the characteristics of each other section of pipe work, because the pressure drop overall has changed. It may impact the velocities in other areas. It may impact the mass flow in other areas. So it can be quite a repetitive task. It's okay for systems that up to, I was going to say up to sort of 6 fixtures. Depends how patient you are. You can do 100 fixtures in an 80,000 square foot store. I wouldn't want to, but you could. But it's also that time of having 5 working days dedicated to doing that, and then when a revision comes through, potentially doing it all again. Yeah, it's how patient you are and how quick you are identifying similarities and rules of thumb. So going back to this, let's say, for example, we found that our pipe size between the evaporator there and the condensing unit was 3/8. And that could well happen on site because the suctions between those two cabinets, the 6 foot and the 12 foot, may only be a 3/8 suction. And then it may be a 3/8 suction coming off of that evaporator. And then people may assume, well, because they're all 3/8, we can continue with that. But actually, no, now you've got additional mass flow coming from that evaporator. And then we need to step it up in size. Another way to check if that's too small or too low is we could go actually measure our suction pressure of the compressor and check it's, say it's 24.7 bar gauge or 360 psi. Well, if we know what evaporating pressure is at our evaporators, and when we can compare that to the difference, if it's drastically lower, then it probably is a restriction. I say a restriction, undersized pipe, because we're now getting excessive pressure drop.
And this is where I've seen it many issues where that's exactly how you figure it out. You take it from the last evaporator, for an example, and then you go do it at the inlet of the compressor, where I've had people tell me they had like a 12 psi or almost 1 bar pressure drop. They're running into oil issues, and that's how big of a pressure drop they have in their suction line going back to their condensing unit, or to that to the condensing unit. So it's something that and that's a quick check. Like, you can go in, and now today with CO2 systems, we got pressure transducers on almost all the evaporators. Well, we do have them on all of the evaporators, so you can compare that to your suction header pressure.
Yeah, it can be quite drastic. When you say 1 bar, 15 psi pressure drop, if that was on the HFC system, well, you haven't got any chance of your compressor's running accordingly there. If you're on a low temp 404A system, you'd be running nearly in a vacuum at that point. Got 2 questions here just before we move on to the next slide. Fitting quantities normally counted during design, or an allotted percentage estimated during design, and then the actual quantities counted when the project is being installed to assure we are staying within the design criteria? Yes, so there's 2 ways I've seen of this generally, is you multiply your pressure drop by, say, an additional 15% to account for that as a rule of thumb, or if you have a software and you input a target pressure drop of, say, 2 Kelvin on the suction or 1.5 Kelvin, you then set that at a level low enough that actually, in reality, it might be slightly more than that. But at least you know that your pipe sizes aren't going to drop your saturated suction temperature below what it needs to be. So a good rule of thumb, or I say a good rule of thumb, The bare minimum, I would say, is a 2 Kelvin pressure drop, should be 3.6 Fahrenheit.
Yep.
That should be the most pressure drop you really get, because at that point you're getting, you're throwing money away in terms of reducing the efficiency of your compressors. But if you try and design all your stuff around half of that value or 75% of it, and don't factor in any of your bends or fittings, etc., any of that which does actually occur in real life, you haven't had to model, but you can be fairly confident it won't drop it below what your actual saturated suction temperature needs to be. And then following on from that, another question, is it good practice for a fast calculation to use the piping module in Cool Selector instead of components in series? Yes, definitely. Based on what we've just said, as long as you allow a little bit extra leeway on your overall pressure drop, we can assume that, well, you don't have to model this 90-degree bend here, here, here. And I'll just slide back to, oh no, don't think I've got it in here. I've not shown the actual section of it, but this table here in the top left was based on the piping module rather than the components in series. And it gives you 1.1 for the section which we used versus, well, here we are, 1.1 here as well. Even better. So what our solution for this would be, if we had that as 3/8 inch, we'd increase the pipe size. I imagine 90% of people out there, technicians, would come to that same conclusion as well. If it's too small, you make it bigger. Up you go.
The thing is that we don't do that as much, you know what I mean? This, as a technician, we're taught, okay, let's go out and do a service and we got to fix a mechanical problem. Maybe it's an electrical issue. But sometimes design mistakes happen. Don't complain and cry about it. We got to fix it. This is it. Nobody's there but you. At the end of the day, it's you that has to fix it as a technician. And it's important to learn this stuff. I think I am a better technician now is because I'm learning design and engineering behind why something happens. If you're running into an oil issue, there's a reason why. Don't just keep adding oil, like Chris said earlier. We got to figure out why the oil is gone. If it leaves and doesn't come back, it's somewhere in the system. Unless there's a leak, that's your first step, and that's usually obvious. Sometimes it's not, if it's in the attic or on top of a walk-in box, but most of the time, it would be obvious on oil stain somewhere. But if you don't see any of that, that oil's still in the system somewhere.
Definitely. To be fair, Trevor, you've just touched on the first point there as well with this slide. Does the system show signs of low oil but no oil leaks are visible? Is one fixture or row of fixtures not achieving temperatures whereas others are? At least we can then pinpoint it down. Generally, if one part of it's running, or let's say that oil is actually back up in our compressors correctly. I would say we've added oil to the system recently. It's still in our compressors. A handful of cabinets aren't down at temperature and they're still not achieving temperature, whereas all the others have. It could well be a piping issue. Could still be loads of oil trapped in that section of pipework, down in those evaporators, coating them all. And basically, the more oil we have down there, the less heat transfer we're going to get into our refrigerant because it just coats the surface of those evaporated coils. And you'd need to have twice the airflow to get the heat into it, which, well, those evap fans aren't going to change. So all you're going to do is get half the cooling, and therefore it's not going to achieve temperature, and then you can get all of your alarms happening instead. Another side of this is one fixture on a row not achieving temperature when the other fixtures are satisfied, or if they're defrosting. Well, that could well be a case that oil is trapped inside that system, or it's not being able to force its way back up our riser, back to our suction pipe and carry on the flow. So it could well be a case that an oil riser is insufficiently sized or it's not present at all. So a bit about the design on these. We have a downward curve at the bottom and an upward sweeping bend at the top. The bend at the top is so once oil makes its way up there, it doesn't have a way to drop back down. Say it falls out or the mass flow drops, and there's not as much refrigerant flowing through that's top section, but the oil's still sat in that pipe, it could possibly work its way back down. Good practice is to design suction pipe work with a slight slope back to the compressors, or to the next point of the next oil riser. The bottom section, as the process carries on, oil starts to fill up that trap, and it will basically trap until it reaches a point where it can no longer go through this seal. So let's say it makes a nice flat oil trap. As any trap below your sink in your kitchen, you have water in there to stop smells coming back. Well, same principle here. We want to make sure that gas builds up behind to enough velocity to then dislodge that oil and force its way up. Normally, we design this based on a certain velocity. So with HFC, you'd typically seen velocities of sort of 12 meters a second to 20 meters a second plus. It should be 2,400 feet per minute to 5,000. CO2 is a lot more forgiving in a sense. You can get oil entrainment at much lower velocities because of the denser suction vapor, in effect. It entrains oil very well. We've run some calculations. I mean, again, it's effectively 2.5 meters a second lower than HFC to carry that oil up. Obviously, that's dependent case by case, but almost as a rule of thumb, you can have velocities 2 to 3 meters a second lower, which would be 100 to 300 feet per minute lower as well, or up to 600 feet per minute lower, sorry. Rule of thumb previously was to step riser size down by 1 size compared to the horizontal sections. And also other people I've ran across quite a good rule of thumb, up to 3 fixtures on a single riser. Above 3, we switch to this double riser configuration, which is shown on the right-hand side here, and operates very similarly. The oil riser still needs to be sized so it can accommodate full mass flow for those fixtures connected to it, but also be sized small enough that at low load, say if we had a row of 10 cabinets, only 2 of them are running, well, we need to only carry 1/5 of the flow through it. Well, that might not be enough to return oil up that riser at low load, but if we sized it smaller, we'd have an excessive pressure drop here and have a negative impact on our system or at our compressors. So what we can do is put this double riser in instead. This oil trap at the bottom will fill up, and if we only have 1 or 2 fixtures connected to it, what they'll do instead is find their way up through here. If we only have a handful of fixtures, we're not worried about oil returning at that time. Once the rest of them turn back on, it will flow back through that main route and it will carry on as normal. But we still want that suction gas to rise up this point here. So why don't we do this on every system? It's a lot more pipe work. It's very difficult to make look tidy as well, which I know a lot of end users, particularly their merchandising teams, unless you have large boxing in, you're going to have to look at what most people would see as a mess of pipes. I think they look pretty good, to be fair. We don't see them very often in the UK, and particularly not on CO2 systems. So when you do come across one, possibly left over from HFC, it's quite a special thing to see. But I just think it's a great engineering solution. So sizing that,
I only seen a few of them out there myself in the supermarket industry. You don't see it too often. Rarely.
No. I mean, much larger, you're talking 40,000 square foot stores and above, where you have possibly 12 open-fronted display cabinets on a single riser. You can get some large swings in duty there. If some at temperature, if night blinds are down overnight, or somewhere on defrost, and you still need a decent amount of product being cooled in the grand scheme of things, it makes sense to go down this route here. So how can this ideally help you as a technician on site? Well, a couple of questions to ask yourself is, has it been present since startup? Have you always suffered with this building? Have the store management say, well, it's been doing this since day one? They'll say that for everything, regardless if it's brand new or not. But at least you might sometimes get a straight answer from them. If it is yes, it's probably pipework related, or it may well be. But then If it's not, has work recently taken place which has changed that pipe work? Have they moved some cabinets? Have they added some onto the system? Well, it could be an issue with duty, or it could be a case of now that island was there, now it's there. But instead of connecting to that section of high level pipe work, it's connected to that one, and that's two sizes too small now. Yeah. Ideally, you should have some isometric pipework schematics and you might be able to trace them, but again, probably not. Some of these stores could be 15, 20 years old, but they're still having work done. So go back to these sort of first principles and almost common sense. If something looks wrong, you'll probably know it from experience. You carry out your normal checks. So check your control settings, your pressures, your temperatures, your run current, your oil, liquid levels. Go back to what we spoke about earlier. Check the evaporating temperature of some of the display cabinets, and then check it at the compressor. See how much of a difference there is, how much pressure drop is there. If it is an excessive amount, it's probably a pipe size issue, or you'd have a restriction somewhere. You're not likely to get a restriction in the suction pipe. So it's probably the suction pipe itself is the issue.
I
Rule
have
out those
seen though,
typical.
Chris, though, like people, adding systems, not on a CO2 one, but adding systems and just using soft copper and pulling it across, the thrusts. And then, it goes like this. So you got like a couple dozen oil traps all the way along, which causes major issues to a system. So don't do that. Don't do that.
Ideally, don't use soft copper at all on CO2. I think there
Yeah,
are bigger issues there.
yeah, for sure. That was
Uh,
definitely an HFC system, but
But yeah, I mean, again, all we've discussed today isn't specific to CO2, but it might actually be more difficult to spot on CO2 because it can be a lot more forgiving on pipe sizing. That's purely because it's such high pressure. One one bar of pressure drop is only about 1 Kelvin equivalent temperature or 2 Fahrenheit, whereas HFC, if you lost a whole, 1 bar of 15 psi on hole 404, you changed it from a medium temp system to a low temp system almost
yeah,
immediately.
yeah.
So it's known about refrigerant. Again, Danfoss is really helpful for this by their I think it's called Ref Tools, their
Yeah,
app.
ref
Can't,
tools. Yeah.
yeah, excellent. I mean, it has a refrigerant slider, the comparator for any refrigerant you're realistically going to use out there. So you can go through bookmark some of the preferred refrigerants if you work with them on a daily basis. I think I've still got 134A and 404 on there from whenever I came off the tools, it's talking 7 or 8 years ago. Yeah. I don't think there's probably a 404A system out there to work on nowadays. Well, hopefully not anyway.
There's less and less
Just
of
going
them, that's
back
for
to it.
sure.
Yeah. Is the fault present across the entire system? If it is, you can narrow your scope down, search from that trace by what is the last fixture before it gets back to the compressor. If you rule that out, well, it may not be pipe sizing, or unless you've got excessive pressure drop from that point back again, and then start breaking into sections. As we do any fault finding, you try and break one large piece down into smaller sections until you get to either that is the issue or you can rule that out. So again, ask yourself questions. If yes, check the pipe sizes between the closest fixture and the compressors. If not, check the pipe sizes on just those fixtures which aren't achieving temperature. And sometimes the only way to be sure is to go back to first principles and design the system in line with best practices. But as a technician, you shouldn't be expected to do that. You should expect that those who have designed the job, signed off on it, installed it, did their due diligence and installed it. But there's always changes, as we said. A brand new system, they have no excuse. If it's 20 years later, and maybe someone else has come in, someone else come in, someone else come in, move some cabinets, change some controls, maybe, and messed up something. It could well be pipe work related. Just do your due diligence as a technician and just check it over. Rule it out. At least you know that's not the issue, and then you can start getting back to looking is it one component I need to sort? Great. Is it an electrical fault? Great. And deal with that. You're not having to repipe 30 feet worth of high level services. It can be a big task to repair, which to be fair is why it requires some thorough investigation. So that brings us to the end of that one. Does anyone have any questions? We've had questions as we go along, but it's welcome anymore.
One of the things is, even in our design course that we just finished, our fundamentals design course, we had one of the designers in there talking about a system that was 20 years ago, and they designed it 20 years ago correctly to those conditions, but now 20 years later the ambients are different. They're getting different temperatures um, from that design. So now they're looking at it that they're not meeting capacity in the middle of the summertime because it's hotter summers than it was when they designed it the first time. And we're seeing this around the world. Even Chris, we talked about this multiple times. In the UK, the temperatures are changing where you don't really have conditioned air in a lot of the markets there. Where here we have conditioned air because of winters and stuff. But we're seeing that more and more. You might have designed a system 20 years ago, but now the conditions for that same system are different.
Not necessarily pipe sizing related, but I had one where there's a brand new fish counter in an open market, effectively inside a building, peak summer. So you're talking probably in that place it was 35 Celsius plus. It was hot. Specimen, I don't like the heat. I was sweating in there going in to fix it. Brand new piece of equipment. Someone had installed it. It was an imported piece of equipment, so I had to ring the manufacturer. They basically checked, that plate evaporator should be suitable for this temperature and this product. But where the condensing unit underneath hadn't been installed as per the original design, it was actually only probably another 20 feet away. But that additional suction super it was picking up between that point and there was just pushing it outside its operating envelope. Discharge temperatures are, didn't quite get burned off of it, brushing my hand, but it was getting to that point. You're talking 100 Celsius plus easily, a 404A system. It was, that was sort of my first introduction to the difficulties with where pipework goes to and how it can actually impact the operation of the system more so than just, that one's cheaper or whatever. And I never understood why we sized pipework like that. And after that, actually probably sparked my interest in that. And then it got me into the rest of the design field. But it only takes one job like that, which is a bit out of the ordinary, as a solution to get into a bit more, I wouldn't say an engineering mindset, because we all have that. But in terms of, is it something which isn't just easily replaceable? It's not something that has failed on the system, but has never worked right on the system. Or it has worked right, but now we're in certain conditions where the only thing to do is change the system. It's a bizarre.
And it
You don't come
happens.
across it very often, I must
Yeah.
say, but it does happen.
And that's the thing about piping on the roof. Like I've done so much, you put a condensing unit up on the roof and you have to pipe to it. That insulation, if you're 150 degrees on the roof, you got to take that into consideration. Even though you have insulation, you should probably make it thicker. Make it thicker. If they say it's a 3/4, maybe you should put an 1.5 or whatever on it, because if it gets that hot on the roof, and depending on what the materials on the roof, it could make it 20% hotter up there. Jason has some good points too about improper slope of suction lines, lack of traps or risers, kind of like we talked about, reduced on traps when they should be, especially on low temps when velocities are lower, for sure. Definitely those things you got to look at as well when you're doing your install. And to Robert's question earlier, talking about inverted traps, there's a few things. I don't know if it's done on CO2, but I know a lot of, especially the manufacturers here in Canada. One of my good friends, Peter, from Keep Right, he sent me some pictures. He's been doing design for decades. This guy, super smart. His name's Peter Frame, and he sent me some pictures of inside these headers, and he designs his with something called quills, which is kind of an inverted trap. So you just say you have a 6-inch header or a 4.5-inch header on your rack. The suction pipe actually comes up into the header, and so it sticks up maybe 3 inches into the header. And then there's a little hole for oil to get back. But I think that might be, I don't know, Robert, if that's exactly what you're talking about, but that's what I could see as an inverted trap. So any liquid coming back doesn't just get jammed right into the compressor.
Yeah, we've done that before, but specifically with transcritical CO2. As I did the training classes a few weeks back, I went through the training guides for carriers disposition. And for me, being in the field quite some time, it was new to me to know that our transcritical CO2 actually has an inverted trap at the compressor, which hasn't been standard through HFC models, right? And the other big thing was in the piping portion, as you talked about insulation and picking up heat. Um, I've seen a lot of not not insulated drop legs from the condenser, whether wherever you're at, whether adiabatic, right? And you're picking up that heat in that drop leg. And one of those first things, like you said, we have transducers is you're that all that subcooling that you're getting, depending on where your region is, gets wasted and infiltrated. So those are just two key points recently that I realized that in the old days we had critical charge systems, but just recently I've been in the forefront of the literature of inverting suction piping from liquid migration on transcritical CO2 at the compressor. The one you're referring to is on a suction header, of course. Yep, we've seen that before, but specifically that inversion. And then the second is liquid insulating the liquid line or drop leg from the condensers, right?
I
To
totally
keep
agree with
that
that.
subcooling in the liquid.
I've seen so many too, and I asked those questions multiple times, like, why isn't this insulated? Because I've even seen discharge lines insulated now on transcritical CO2 systems, different lines being insulated to try to keep as much cooling or heating in the system, or compressors insulated, where you've never really seen that on an HFCI system before, but now I'm starting to see different methods of efficiency. But that's a big one you said there, Robert, was that insulation on the drop leg. Because if you have the drop leg and it's 120 out, yes, you're still trying to maintain 94. I don't know the behind the scenes for that, maybe in the winter time. Chris, any thoughts on the drop leg being insulated?
My experience with CO2 is we insulate every inch of pipe work anyway. The discharge pipe which should be insulated just to as a safety precaution in effect, and also a lot of the systems I've done, we've wanted to capture any heat for heat recovery, so it makes sense to keep it in the system and use it elsewhere. And then in terms of once it exits that, I suppose in periods of subcritical operation, it's then going to go straight through that HPV and drop down again. It would be odd to insulate up to that point before it then gets insulated before it goes into our receiver or flash gas vessel. I've never really thought about the thermodynamics behind it as such, but it's more of almost an aesthetic consideration. Why insulate the rest of your system and not one small section of pipe work would be my argument. But yeah, it makes sense to in terms of you want to keep that heat in the system unless it's going out at a heat exchanger or a gas cooler, in my opinion.
I love it. Chris, I want to thank you taking the time to share your knowledge with us, your wisdom. I know that you've designed so many systems and you've worked in the field as a technician. I really appreciate you taking the time to come on CO2 Experts and share that knowledge with us. And I look forward to for the next CO2 Experts that you come to and share your questions. Send some questions in. Send your message. If you're listening on to the podcast, get over to the YouTube channel and watch the video. So the slides that you see that Chris went through, because I know sometimes people reach out, it's like, oh, Trevor, I don't really understand listening. I need to see, I got to touch, I got to feel. I'm the same way. I got to be out there working on the equipment, seeing it, touching it. So if you're listening on the podcast, definitely head over to the YouTube channel to watch the video and the slides that Chris just went through. The more you learn, the more you invest in yourself, the better you're going to be. And share this knowledge. One of the things I'm always telling all the people in my community, all the people that I'm training, is you got to share this knowledge. So what we're talking about here today, for you to understand it to the best of your ability, is actually sharing it with other people, going out and talking about it, sharing that knowledge. And this is how we get better. This is how we uplift the industry. This is how we all get better at the refrigeration collectively, is really sharing our knowledge with others. Yes, there's competition out there. Get different contractors, different manufacturers, different end users. But at the end of the day, we're all in refrigeration. We want to make it better for all of us, the industry. And this is what this is what we're doing here. I want to thank you, Chris, one more time for coming on CO2 Experts, and I look forward to seeing you all at the next one. Thank you guys so much.
Yeah.